Right now, while you are reading these words, a machine the size of a small car is sitting more than 15 billion miles from where you are standing, and it is still talking to us. It should not still be talking to us. It was built in the 1970s, before the internet, before home computers, before almost every scientist currently working on its data was even born, and it runs on less power than the bulb inside your microwave. And yet, right now, in the summer of 2026, this machine is at the center of one of the strangest, most tense chapters in the entire history of space exploration, a chapter almost nobody outside a small team at NASA is paying attention to. This is not old news being recycled. This is happening this month. A risky, unprecedented engineering procedure is being tested on it right now. A countdown to a historic milestone is ticking down to an exact second in November. And the spacecraft itself has already forced scientists to admit, in their own published words, that something about the space between the stars does not behave the way any model ever predicted. Stay with me, because by the end of this, you will understand exactly why engineers at NASA are holding their breath this week, waiting for a signal that takes almost a full day just to arrive. If stories like this are the kind of thing you want more of, go ahead and subscribe now because we are only getting started. Let's go back to where this actually begins, because the origin of this story is almost impossible to believe on its own. On September 5th, 1977, a rocket lifted off from Cape Canaveral in Florida, carrying a spacecraft that NASA expected to work for about 5 years. The mission was modest on paper: fly past Jupiter, fly past Saturn, take pictures, gather some data, and then go quiet somewhere around 1981 or 1982. That was the plan. What actually happened turned into one of the greatest engineering stories human beings have ever written. The spacecraft, called Voyager 1, flew past Jupiter in March of 1979 and sent back the first truly detailed images of that planet that human eyes had ever seen. It reached Saturn in November of 1980, using the gravity of each planet like a slingshot, picking up speed with every pass. And then, instead of going quiet the way NASA expected, it just kept going. By the end of the 1980s, it had already become the most distant human-made object ever launched, and it was still transmitting, still functioning, still running on hardware that modern engineers look at today and shake their heads over in disbelief. Then, in August of 2012, 35 years after launch, Voyager 1 did something no human-made object had ever done before. It crossed the heliopause. If that word means nothing to you, here is the simplest way to picture it. The sun does not just give us light and warmth. It constantly blows out a stream of charged particles called the solar wind, and that wind pushes outward in every direction, forming a massive protective bubble around our entire solar system. Every planet, every moon, every spacecraft we have ever launched, and every living thing that has ever existed sits inside that bubble. The outer edge of it, the point where the pressure of the solar wind finally gives way to the pressure of the actual galaxy pressing in from outside, is called the heliopause. It is the real physical boundary of our solar system. And in 2012, Voyager 1 crossed straight through it and came out the other side, becoming the first thing our civilization has ever placed in the actual space between stars. It kept transmitting the whole time. We had, for the first time in human history, a live instrument sitting outside our own solar system, and it was about to tell us that everything we thought we knew about what was out there was incomplete. Here's where the first real twist enters the story, because for decades before Voyager 1 got anywhere near that boundary, physicists had built detailed models predicting what interstellar space should look like. These were not guesses scribbled on a napkin. They were serious, peer-reviewed models built by some of the best minds in the field, and they all agreed on the basic picture. Interstellar space should be calm, thin, cold, mostly empty, a quiet gap between star systems where not much happens. Voyager 1 flew into that supposedly quiet gap and found something completely different. Starting around 2017, the plasma wave instrument on board began picking up a signal nobody expected. A faint, steady, persistent hum inside the interstellar plasma. Not a single burst that could be explained away as a glitch, but a continuous emission that kept showing up year after year. A team at Cornell University, led by a doctoral researcher named Stella Koch-Ocker, working alongside astronomers James Cordes and Shami Chatterjee, studied the signal in detail and published their findings in the journal Nature Astronomy. Their conclusion was blunt. Interstellar space is not the smooth, silent void the models described. It has structure. It has motion. It is, in a very real physical sense, active in a place nobody had ever been able to listen to directly before. One of the researchers compared it to the difference between hearing a single clap of thunder during a solar storm and then hearing a steady, gentle rain in between those storms, a background hum of the galaxy itself that nobody knew was there because no instrument had ever been positioned to hear it. Now stop and actually sit with that for a second, because this is the part people scroll past too quickly. Every single model of interstellar space that existed before this discovery was built from the inside, looking out, using telescopes and mathematics and theory from right here on Earth or in Earth orbit. Nobody had ever had a working sensor actually sitting out there to check the math against reality. And the first time we finally did, the answer we got back was that the models were missing something. That does matter to you, by the way, and not in some abstract, faraway sense. The heliopause, the very boundary Voyager 1 crossed, is not just a line on a diagram. It functions as a shield. It deflects a huge portion of the most dangerous high-energy cosmic radiation, the kind that comes screaming in from exploded stars elsewhere in the galaxy, keeping it from reaching the inner solar system at full strength. If the environment pressing against that shield from the outside is more turbulent, more energetic, and less predictable than our models assumed, then the long-term behavior of the shield protecting every living thing on this planet becomes a slightly more open question than it was before Voyager 1 got there. Scientists are not panicking about this. Nobody is telling you the sky is falling. But the fact that serious researchers now have to ask the question at all, using real measured data instead of theoretical assumptions, is itself a meaningful shift in how we understand our own exposure as a species. There's another layer to that heliopause crossing that rarely makes it into casual conversations about Voyager, and it deserves a moment of its own before we move forward. For decades, the models describing that boundary predicted a slow, gentle transition, something closer to the way a river gradually blends into the sea, with the hot solar wind on one side, thinning out calmly as the interstellar medium on the other side slowly took over. That is not remotely what Voyager 1 actually measured. At the heliopause itself, particles were not drifting apart peacefully. They were slamming into each other at speeds approaching a meaningful fraction of the speed of light, generating temperatures that researchers estimated at somewhere between 30,000 and 50,000 degrees. Not inside a star, but at the outer edge of our own solar system, in a region that was supposed to be cold and mostly empty. Some scientists studying the data have described this narrow region using a phrase that sounds almost too dramatic to be real, calling it a wall of fire, and they mean it fairly literally. An intensely energetic zone of charged particles forming a genuine physical barrier at the edge of everything we call home. On top of that, researchers found something else nobody expected, involving magnetism. For years, the working assumption was that the sun's magnetic field and the wider magnetic field of the galaxy were two separate systems, cleanly divided at the heliopause. Instead, Voyager 1's instruments showed the two fields lining up and interacting directly with each other through a process called magnetic reconnection, in which field lines from different sources rearrange themselves and release energy in the process. In plain terms, our solar system is not magnetically sealed off from the rest of the galaxy the way earlier models assumed. It is linked to it, actively exchanging energy across that boundary in ways nobody had built into their calculations before Voyager 1 actually got there and checked. Before we go further into what is happening with Voyager 1 right this month, it is worth understanding just how badly this mission nearly ended, because it shows you exactly what kind of team keeps this ancient machine alive. In November of 2023, Voyager 1 suffered the single worst failure of its entire mission. It kept transmitting a signal, but the signal was gibberish, corrupted, unreadable, even to a team that had been decoding the spacecraft's data since the Ford administration. For nearly 5 months, engineers at NASA's Jet Propulsion Laboratory worked the problem with almost nothing to go on. The cause, once they finally traced it, was almost poetic in how small it was. A single memory chip, a physical piece of 1970s hardware smaller than a fingernail, had degraded after roughly 46 years of continuous exposure to cosmic radiation, corrupting the exact section of code responsible for formatting and sending data back to Earth. There was no way to fly out and replace it. The nearest human being was billions of miles away. Every single command sent to the spacecraft took over 20 hours just to arrive, and the response took another 20 hours to come back, meaning every single test of every single theory cost the team the better part of 2 full days. Think about what that actually means for how you do your job. You form a hypothesis, you write a fix, you send it, you wait almost a full day, you get a response that tells you something slightly different than what you expected. You revise your theory, you send it again, you wait again, and you do this patiently for months, knowing the entire time that one wrong instruction sent across 15 billion miles could end the mission permanently with zero chance of recovery. In the end, the team did not repair the corrupted code. They relocated it, splitting the affected software into smaller pieces, storing them in different parts of the spacecraft's remaining memory, and carefully reconnecting everything so it functioned as a whole again. It was, in every meaningful sense, remote brain surgery performed across a communication delay of nearly 2 full days on a patient that launched during the Nixon administration. By mid-2024, Voyager 1 was back, sending clean, complete, readable data again. If a team could pull that off, you start to understand why nobody at NASA is willing to call this mission finished, even now, even in 2026, even as the spacecraft's power keeps draining away. And that brings us to what is actually happening right now, this month. because this is the part of the story that almost nobody talking about Voyager Online seems to know. Voyager 1 gets its electricity from 3 radioisotope thermoelectric generators, essentially small containers of decaying plutonium-238, whose heat gets converted into usable power. At launch in 1977, those generators produced somewhere around 470 watts combined. Today, after nearly 50 years of steady radioactive decay, that number has fallen to somewhere around 250 watts, and it keeps dropping by roughly 4 watts every single year, a slow, mathematically certain decline that nothing can stop. Of the 10 scientific instruments Voyager 1 originally carried into space, only a handful still function, and the choices about which ones to sacrifice have become brutal. In April of 2026, engineers made the call to shut down the Low Energy Charged Particles instrument, a device that had operated almost continuously since the year of the spacecraft's launch, one of the very tools that had helped scientists confirm exactly when Voyager crossed into interstellar space in the first place. The instrument itself was not broken. It was simply too expensive to keep running. And to make matters worse, an unplanned power drop hit Voyager 1 back in February of 2026, following a routine maneuver, leaving the spacecraft in noticeably worse shape than its twin. Here's where I want to slow down and be honest with you, because this is exactly the kind of moment where online headlines tend to run wild, and I would rather give you the real, careful version than the exaggerated one. Over the past couple of years, you may have seen articles claiming Voyager 1 detected something truly impossible out there. Language hinting at alien megastructures, mysterious barriers, even whispers from another dimension. Almost none of that reflects what the actual scientists working on this mission are saying. What is real is this. Back in 2020, Voyager 1's magnetometer picked up a sudden jump in the strength of the magnetic field within the interstellar plasma around it, paired with a rise in plasma density. Similar spikes had shown up before and settled back down within a matter of months, the kind of thing researchers like Adam Sabo, an astrophysicist at NASA's Goddard Space Flight Center, compared to a piston, a pressure wave from an outburst on the sun, traveling all the way out to interstellar space and rattling the plasma like a slow-moving shockwave. But the anomaly that began in 2020 did something the earlier ones did not do. It did not fully settle back down. That single fact, an elevated magnetic signature that lingers rather than fading, is genuinely unusual and genuinely still being studied. It is not evidence of an alien structure. It is evidence that our models of how disturbances propagate through the boundary of our solar system are still incomplete, which, if you have been paying attention through this whole story, should not surprise you at all by now. Now, back to the engineering drama actually unfolding this month, because this is where the story gets tense in a very real, very immediate way. Knowing that the power budget on both Voyager spacecraft keeps shrinking no matter what anyone does, the team at the Jet Propulsion Laboratory has spent the past couple of years designing an experimental fix, something they nicknamed, only half-jokingly, the Big Bang. The idea is to reconfigure how power flows through the spacecraft's remaining systems all at once, in a single coordinated operation, rather than adjusting things gradually. Specifically, it means shutting off certain devices, like dedicated heaters and an old tape recorder kept running purely for the leftover warmth it generated, and replacing them with lower power alternatives that draw less electricity while still keeping the spacecraft's propellant lines and instruments from freezing solid in the cold of interstellar space. The reason for doing it all at once, rather than one small change at a time, comes down to risk. During any partial reconfiguration, the spacecraft passes through in-between states that can accidentally trip its automated fault protection systems, which are designed to start shutting things down on their own the moment they detect the power draw exceeding what the generators can supply. The engineering team wanted to minimize the time spent in that dangerous in-between zone by making every change simultaneously and getting through the transition as quickly as possible. It is worth pointing out here that Voyager 1 does not carry this mission alone. Its twin, Voyager 2, launched 16 days earlier in August of 1977, despite carrying the higher number in its name, because it was sent on a longer, more complicated route past all 4 giant planets, Jupiter, Saturn, Uranus, and Neptune, a feat no other spacecraft in history has matched before or since. That longer path meant Voyager 2 reached the heliopause 6 years after Voyager 1 did, crossing into interstellar space in November of 2018 rather than 2012. But Voyager 2 carried something Voyager 1 no longer had by that point, a working plasma science instrument, since Voyager 1's own version of that instrument had quietly failed decades earlier, long before it ever reached the boundary. That difference matters enormously, because it meant Voyager 2 could directly measure the temperature and density of the plasma on both sides of the heliopause as it crossed, filling in a gap in the data that Voyager 1 alone could never have closed. Today, Voyager 2 sits roughly 13 billion miles from Earth, a little closer than Voyager 1, and running with a slightly larger power margin, which is exactly why it became the test subject for everything that has unfolded over the past several months. Because this had never been attempted before, at this distance, on hardware this old, the team chose to test it first on Voyager 2, which has slightly more power margin and sits somewhat closer to Earth, making it the safer subject if anything went wrong. A power test on May 13th of this year confirmed the reconfiguration would not draw more electricity than expected. Additional power and thermal tests followed through May and June. Then, on July 9th, 2026, engineers executed the full procedure on Voyager 2. They turned off 2 dedicated heaters and a tape recorder that had been supplying only residual warmth, and switched on 2 different lower power heaters along with another low draw source of heat, all timed together in a single coordinated sequence across a communication delay of roughly 20 hours each way. According to NASA's own statement on the result, the fix worked, and without it, the mission would have been forced to shut off yet another one of Voyager 2's 3 remaining science instruments before the end of this year. Instead, the savings from the Big Bang procedure should keep all 3 of Voyager 2's instruments running for at least an extra year. That success is exactly why, right now, this week, engineers are running the same nerve-wracking procedure on Voyager 1. A power test was completed on Voyager 1 at the end of July, and according to the team, it went, in their own words, remarkably smoothly. A thermal test is scheduled for the end of August, though the exact timing could shift depending on how the data comes in. If everything continues to go well, the full Big Bang reconfiguration will be attempted on Voyager 1 in the near future. And here's the detail that makes this genuinely exciting rather than just a technical footnote. When engineers shut down the low-energy charged particles instrument back in April, they deliberately left a tiny half-watt motor inside it still running. A small, quiet decision that leaves the door open for that instrument to potentially be switched back on if the Big Bang frees up enough spare power on Voyager 1. Nobody at NASA is promising that outcome. The team has been careful and measured every step of the way. But the mere fact that they built in the option tells you everything about how this mission has operated for nearly 50 years, refusing to fully close a door until it is absolutely forced to. If any of this is making you appreciate just how much quiet, patient human effort goes into keeping 50-year-old hardware alive across billions of miles of empty space, drop a comment and let me know, because it genuinely helps guide which stories from this mission we dig into next. It is also worth pausing on who is actually doing this work, because it is not a large team, and it has never been a large team. Many of the original Voyager engineers retired years ago, and the people who took their place had to learn programming languages and spacecraft architectures from an era before their own careers even began, simply to keep speaking to these machines in the language they were originally built to understand. That kind of knowledge does not live in a modern textbook. It lives in the heads of a small group of specialists at a single facility, passed down individually, refined through decades of hard-won experience, solving problems nobody else has ever had to solve, because nobody else has ever operated hardware this old, this far away, for this long. Now, let's talk about the date already locked onto the calendar, the one that is coming whether the Big Bang procedure succeeds or not, because it is arguably the single biggest milestone in the entire history of human spaceflight, and most people have never heard of it. On November 18th, 2026, at 2:16 and 7 seconds in the morning, Pacific Standard Time, Voyager 1 will reach a distance of exactly 16,094,799,096 miles from Earth. In more useful terms, that is the distance light itself travels in 24 hours, one full light day. No human-made object has ever been that far from home, not once, in the entire history of our species building things and sending them outward. Right now, in the summer of 2026, a command sent to Voyager 1 already takes roughly 23 hours to arrive, with the response taking another 23 hours to come back. So the team is already living inside a nearly 2-day round trip for every single exchange. Susie Dodd, the Voyager project manager at NASA's Jet Propulsion Laboratory, described the reality of this delay about as plainly as anyone could. If she sends a command and says good morning to Voyager 1 on a Monday morning, she does not hear the spacecraft's reply until Wednesday morning. That is not a metaphor. That is literally how communication with this spacecraft works today. And by November, that gap widens to a full day out and a full day back. An entire 48 hours to complete one simple exchange of information. Every hour that passes, Voyager 1 travels roughly another 38,000 miles deeper into the dark. There is nothing out there to slow it down. No atmosphere, no friction, no meaningful gravity left to bend its path. Once it crosses that one light day threshold in November, it simply keeps going, carrying with it something that will outlast every single one of us and everything we have ever built. Bolted to Voyager 1's frame is the golden record. A gold-coated copper disc holding greetings recorded in 55 human languages, the sound of rain falling on a forest, the sound of ocean waves, 90 minutes of music pulled from cultures across the entire span of recorded human history, and a diagram made from the positions of pulsars, designed to show whoever eventually finds it exactly where in the galaxy this particular pale blue dot happens to sit. Carl Sagan, who helped design it, called it a message in a bottle cast into the cosmic ocean, and that description still holds up perfectly today. Long after the last signal from Voyager 1 has been received and logged, long after every human city and every archive we have ever built has worn away under the slow pressure of geological time, that record will still be moving quietly through the dark, carrying the sound of human laughter to wherever or whoever might eventually stumble across it. Here is the part of this story that deserves to sit at the center of everything else, because it connects the near-term engineering drama with the much bigger scientific picture. The persistent plasma emission that Voyager 1 started detecting back in 2017 is not just a strange curiosity. According to the researchers who study it, it represents the very first continuous, real-time measurement of interstellar plasma density that our species has ever obtained. Before that discovery, scientists could only catch isolated snapshots of the plasma out there, triggered by rare events like shock waves from solar eruptions finally reaching all the way out to the edge of the solar system. Those snapshots were useful, but scattered, roughly the equivalent of trying to understand an entire continent's weather by checking one single thermometer, in one single city once a year. What Voyager 1's ongoing hum provides instead is something much closer to a continuous feed, a running record of what interstellar plasma is actually doing, day after day, year after year, for as long as the instrument keeps working, and someone remains on Earth able to listen to it. There is still a genuine open question at the center of all of this that researchers have not fully settled. The persistent signal could be coming from thermally excited plasma oscillations, essentially the natural vibration of charged particles interacting with their surroundings, which would be an important discovery but would still fit inside existing physical frameworks without forcing anyone to rebuild them from scratch. Or it could be something called quasi-thermal noise, a different physical mechanism entirely, one that would require real, meaningful revisions to how scientists model the interstellar medium going forward. Telling these two explanations apart requires either more data from Voyager 1 itself, which is producing less of it with every instrument that gets switched off to save power, or an entirely new mission built specifically to study interstellar space with instruments designed for exactly this purpose. No such mission currently exists. No such mission is currently funded. If a spacecraft capable of reaching the heliopause were approved and built starting today, it would still take the better part of a couple of decades just to arrive at the boundary Voyager 1 crossed back in 2012. Which means that whenever Voyager 1 finally does go silent, and sometime in the early 2030s it almost certainly will, the question its data raised will still be sitting there, unanswered. And the only real-time window our civilization has ever had into the space between the stars will close, likely for a generation or more. If this is the kind of deep, careful space story you want more of instead of the exaggerated clickbait version, this is exactly the right moment to hit that subscribe button and turn on notifications, because the results from Voyager 1's own Big Bang procedure, along with everything happening around the Light Day milestone in November, are still unfolding in real time as you are watching this. Step back for a second and take in the full shape of what you have just heard, because it is genuinely remarkable when you put all the pieces next to each other. A spacecraft designed in the era of rotary phones and expected to last 5 years is, right now, this week, being kept alive through a nerve-wracking, never-before-attempted power reconfiguration performed across a communication delay approaching 2 full days. It survived a near-fatal memory failure that took 5 months and a small team of engineers doing remote brain surgery through a computer built before most of them were born. It is heading, on a specific date, already locked into NASA's own calendar, toward a distance so vast that saying good morning and hearing a reply takes an entire work week. And along the way, almost by accident, it became the only instrument our species has ever placed directly inside the space between stars, forcing working scientists to publicly admit in peer-reviewed journals that the universe beyond our solar system is stranger, more turbulent, and more alive with quiet motion than any model built from the safety of Earth ever predicted. None of the far larger, far more expensive, far more advanced spacecraft humanity has built since 1977 have been able to tell us what this small, aging machine is still telling us today, because none of them ever went far enough, for long enough, to actually get there. There are questions about the universe that can only be answered from inside the universe, not from a telescope in orbit, not from a rover on Mars, only from a machine that crossed the one true boundary of our solar system and kept transmitting on the other side. Right now, in 2026, we have exactly one such machine still actively gathering that kind of data, and its twin close behind it, both aging, both fighting for every extra watt of power engineers can scrape together for them, both still sending their thin, patient signal home across billions of miles of silence. As long as that signal keeps arriving, the answers to some of the biggest questions we have ever asked about our place in the galaxy keep arriving with it. The moment it stops, those answers go quiet too, possibly for decades. The signal is still coming, stretched across more than 15 billion miles, delayed by nearly a full day of travel time each way, carrying data about a universe more turbulent, more connected, and more surprising than anything a model built from Earth ever managed to get exactly right. One aging machine, a handful of watts, a countdown already ticking toward a date in November that no human-made object has ever reached before. The only real question left is whether the rest of us are paying attention while it is still talking. If this story is the kind of thing you want to keep following as it unfolds, subscribe now, drop a comment telling me what surprised you most, and share this with someone who would want to know that right this very moment, somewhere 15 billion miles from here, an almost 50-year-old machine is still finding ways to surprise the people who built it.